Hi, in this video we are going to learn about the minimum spanning tree and then how could we calculate it. So first of all, what is minimum spanning tree? So in context of graph, minimum spanning tree is a subset of given graph in which all the nodes were present and some of the edges should be present such that all the nodes are connected and the accumulative weight of all the selected edges should be minimum. For example, this graph is given. If I am talking about the MST of this graph, so when we are talking about the a subset of a graph, it could be calculated by many ways, but in context of MST or minimum spanning tree, we have to pick a special type of subgraph of this given graph. Now that special type is, if this graph is, let's say, denoted by G and set of vertices and set of edges, and we have to calculate a subset of this graph such that all the vertices should be there. So suppose this G1 is a subset of graph and this is denoted by V1 E1. Now the condition for MST subgraph is the relationship between V and V1 is V is equal to V1. So all the member of V should be present in V1 as well as, now for in context of edges, so E1 should be subset of E such that all the accumulative weight of E should be minimum. Now what does that mean? What accumulative weight is minimum? Like this is a graph and the highlighted edges are selected edges. So the accumulative weight means 4 plus 8 plus 7 plus 9 plus 2 plus 4 plus 1 plus 2 is around 38. So 4 plus 8 plus 7 plus 9 plus 2 plus 4 plus 1 plus 2, that is comes to be 38. The accumulative weight of selected edges. Now what does the meaning of minimum here? Like if I am not picking these edges and some other edges, like suppose instead of this edge I have selected this one, and instead of this edge I pick this one. Now the accumulative weight, again the graph should be connected, so all the vertices are there in new subgraph, the highlighted one and these two red edges. Now again this is a subgraph following this particular condition. The vertices are same, the edges are subset of the original edges, but the edges are chosen such that the whole graph is connected, the whole subgraph is connected. But now the accumulative weight of edges are more than 38. It's 6, 7, so 38 plus 7, 45. So now the new accumulative weight is 45. So minimum means if we pick another set of edges, so the new set of edges, cost means the accumulative weight of all the edges, so new set of edges cost should not be less than the MST set of graph, some MST set of edges. So that is what all about MST. Now we are going to calculate how could we calculate the MST. So for that there are two algorithms, minimum the Kruskal algorithm and prim's algorithm. These two algorithms are the example of greedy algorithm. So let's see how could we calculate the MST. So in order to calculate the MST and Kruskal and Prim's algorithm, so these two algorithms are following actually these basic concepts, these basic steps. Now what is the basic steps? And actually you could say this is the basic stuff of Brady algorithm. So initially you, in this particular I am following this particular syntax notations, and these notations are taken from the Codeman book. So initially we take an empty set A, and now what the A is this G1. So when this algorithm completed, the A would be that desired subgraph of the original given graph G. So G is given graph, A would be our solution. Initially A is empty, so initially there is no node or vertices inside the A. Now what we do, we simply like in line number 2, while A does not form a spanning tree, so until we didn't get our complete solution, we continue with this process, step number 3 and 4. Now what does we are doing in step number 3 and 4? Find an edge UV that is safe for A, and then if it is safe, just combine it with the A. So we pick a edge and we check whether it is safe or not. Now what does the mean of safe? Since we are calculating tree, a particular type of tree, and tree is a acyclic connected graph. So since it is acyclic, so when we are considering a new edge, that should not create a cycle with earlier selected edges. So that is the definition of safe here. So if the newly selected edge, newly considered edge is not making circuit with all the previous selected edges, then we could say that this new considered edge is safe. And if it is safe, include this edge into the A. Now this process will keep on going, and when we the spanning tree is created, then we stop this process. Now how could we know that this spanning tree is completed? So there could be many way. Take a note on all the nodes. If all the nodes are inside the A, we could say that MST is completed. Or we could also say take track on number of edges. If we consider all the edges, we might say that the MST is calculated, or any other procedure. So when we notice that all the nodes are included in this our answer, when we then, well, in that case we declare that A is the now complete solution. So now we see how the Kruskal algorithm works. So this is the algorithm, but let first check it manually. How could it be done? So this is a given graph, and we are going to calculate the MST using Kruskal algorithm. Now Kruskal algorithm is simply what does it consider the minimum weight edge. So or consider all the edges and pick the edge which has minimum weight. So in this particular case, the edge HG has a weight 1, and it is not going to make cycle because there is no previously selected edges, so it's not going to make any cycle, so it is safe. So just select this edge, include this edge into our solution. So initially A was empty, so initially V and E1 are empty, but once you select this edge, that means now A become H and G. These are the vertices, and edges are HG. So after selecting this, now after selecting this, just exclude this edge for the all the future references. Now excluding this edge, pick the next minimum edge, minimum weight edge. So for next minimum weight edge, there is a option we have, because next minimum value after 1 is 2. So 2 is present here, 2 is present here, and so there are two options. So you could go with either of these two, but obviously the new considered edge should not create a cycle with the previous one. So here you could go for any of one, because neither this is going to make any cycle nor this one is going to make any cycle. So in this example, this is example of Corman book. So in that particular example, this particular edge has been selected, but you could also go for this one. So that, what does that mean? The final solution could not be unique. It depends on the graph obviously, but if this type of graph is there where the choices are there, or you could say there are multiple edges of same weight, then the final answer could be of different design in the sense the V1 would be same for all the answers, for all the version of answers, but E1 could be vary from person to person or solution to solution. So but the condition is the sum of all the even edges should be minimum. So that would be the condition. So anyhow, we will choose simply this edge. So now the A would become let's say HG, and G are previously selected, and now we have selected I and C, so simply I, C, and the edges are HG and IC. Likewise, in next iteration we pick the next minimum weight. So these two are selected, so we are not going to consider these two edges. Now the next minimum is this 2, so we select this edge. So now this become all this HG. Now this F is also included, so HGF and then I and C. The edges are HG, IC, and this one the GF. So this would be the new subset. So what you could see, initially A is empty. Now after considering one edge, the updated A is like this. After considering the second edge, this is A is updated. After considering the third edge, A is updated, and that's how the A's keep on growing. And once we select all the edges, we could say we have considered all the vertices and we would stop here. So that is how this process will keep on going. Now take a look on the algorithm. Initially A is empty, A would be our solution, G is our graph, and W is for our weight set. So for each vertex V belonging to VGs, so each vertex V of belonging to G. So if our graph is given like this, V and E, so for each vertex make set V. What does that mean? Why does done make set? I'm going to explain this thing in a while. So some processing is done with all the vertices, each and every vertices of the given graph, and then sort the edges of E into non-decreasing order by weight W. Since we are picking the minimum weight edge one by one, so what this algorithm suggests, sort all the edges in on the basis of their weights. So that would be the first edge, this would be second, this would be third, or this would be second, this would be third, and next minimum would be 4. So AB or CF in either of the order, and keep on this process will keep on going. So all the edges will be sorted on the basis of their weights. Now pick the edge one by one, obviously in the order of their weights. And now the definition of safe. If it is safe, what does that mean? If it is not making cycle with the previous one, how could we check it is not newly considered edge is not going to make cycle with the previous one? Now this make set is coming into the picture, make set and find set. So this line number 6 and line number 3 are designed for how we going to calculate, how we going to sense that whether the newly considered edge is going to make cycle or not. So if it is not making cycle, just include that newly elected edge or considered edge into the A and combine this UV. So what does that mean? These line number 3, 6 and 8. Now I'm going to explain that, but before that just complete this numerical. So in this process will keep on going. So we have selected this 2, and then we are going to select it either AB or CF. So the remaining step of this numerical is like this. So this 2 is selected, and after this 2, this 4 is selected because it is not going to make any cycle. Up to this point we have discussed in the previous slide. Now consider this edge, it is not going to make any cycle with the previous selected edges. So simply we finally include this edge into our answer. Then after this 4, next minimum would be this edge, and this edge is not going to make any cycle with the previous selected. These highlighted edges are previously selected edges. So you could see that this newly selected edge is not going to make any cycle with the previous selected edges. So it is safe, and that's why it is included. Now after this, the next minimum would be this 6, but if we select this 6, that would create a cycle like IGFC, that would make a cycle, and that is not allowed, and that's why this edge is not safe. And if it is not safe, we are not going to include this edge into our answer. So we simply skip that, and we find next minimum after 6. So next minimum would be 7, but this 7 in this particular graph, so 7 is present here and here, but now we don't have choice to choose either of, because this 7 would again create a cycle, and that is not allowed. So this is not going to select. So this time we don't have a choice to choose either this one or this 7 or this 7, because this edge is not safe. We can't include this edge into our answer. So this after this 7 is minimum, so and it is safe, so include it. And next, so in this example it is previously elect or consider this edge and include it, and then this one and reject it. And after this 7, next minimum is 8 is present here and here. Pick either of one. Now which one is selected? Since we have sorted all the edges, so some order must be there. So when we are sorting the edges, either we would put AH before BC or BC before AH. But in this particular example, AH is position first before the BC position in the sorted edges list. So this is considered not making cycle, so included. After this edge is considered, but if we consider this, if we include this edge, that would create a cycle, so this edge would not be included and simply rejected. After this 8, next minimum would be 9, and this 9 is not going to make any cycle, so just include that this edge. After this 9, 10 is there, so if we are going to choose this 10, that would create a cycle, so simply reject that 10. Then 11, it is also rejected, and this 14, that is also rejected. So you could see here all the vertices are selected. Actually we have calculated the MST, but still we are keep on calculating something. Why this is so? Because how does I know that this graph is selected, that MST is calculated? So though there are all the vertices are included in our answer, but we are keep on calculating. So in this algorithm, what they are saying, that for all the edges, for each edges, so they are keeping track of edges. So until unless all the edges are not elected, considered, then this process will keep on going. Another choice could be just keep a track of number of vertices, how many vertices are included into a. If all, suppose there are 9 vertices, so just put a counter 0 and keep a track on this V1 component of the graph. So initially mod of V1 is equal to 0 in the initial of the algorithm, and as the algorithm keep on growing, keep on processing, and this A is keep on growing, then mod of V1 is gradually increases for every iteration of the line number 5. Not every iteration. If the edge is selected, then for every selected edges, the size of V1 is grow by 1. So if we put a track on mod of V1, and when mod of V1 is equal to n, we stop the process. Well, if we would does that, these process could be saved. But why it is not done? It is not done because if we for that thing, for this approach, we should know in advance the size of the graph. So all the mod of V1. So if we know the mod of V1, we could go for that. So but in this Kruskal algorithm, they are using the tracking on the edges. So now, so that is how the answer is calculated. This would be the final answer. You could see the selected edge is not making cycle and all the vertices are connected, so this is MST is calculated. Now one thing is, what is going there in line number 3, line number 6 and line number 8. So let's discuss that. These lines are made for sensing whether a newly considered edge is making cycle with selected edges or not. I am using two words, considered edge and selected edge. Consider mean we are picking a edge and we are watching, we are just sensing whether this edge is safe or not. If it is safe, that edge would be included in the answer. Once included, then that edge would be selected. So considered, we have to consider all the edges, but after consideration it may or may not be selected. So to done the job on the sensing the safeness of the edges, these lines is performed. Now what does that mean? We simply put all the edges as a set. So if there is a graph G and mod of V is equal to n, here in this case 9. So we simply create 9 sets. So there is a set of name A, let's say. There is a set B. So 9 nodes are, or 9 vertices are there in the given graph, so there would be 9 sets. So all the vertices are separate set. So that is done in make set V. For each vertex, make set V means for each vertices or each node, create a separate set. So A is a separate set, B is a separate set, and so on. So I should say like this. So if I am putting set name is this. So name of this set is capital A, name of this set is capital B, and so on. Capital of name of this set is capital H. Now capital A considering only one element, that is small a, the label of this vertices. Now find set V considering, suppose I am considering here this H, like this one. If I am considering the edge BC, let's change the color. If I am considering this edge BC, so UV means this is U temporarily and this is V. So UV edge, if I am talking about UV edge, then set of U and set of V is same or not. So initially when all the vertices are separate set, well in that case B would, the set of B would be capital B and set of C would be capital C, so they are distinct. So if they are distinct, find set U is not equal to find set V, that means it is safe. So if the both end of the vertices, both end of the edge, that is the corresponding vertices, if these two vertices does not belong to same set, then that edge is safe. This line is saying like this, line number 6. Now initially all the vertices are belongs to separate set, then how could the set belongs to same set? I mean B and C belongs to same set, how could it be happen? So what they are doing, if you select some edge, then like if suppose in this previous example what we initially does, like here initially H and G are separate set, H is a separate set and G is a separate set, but if it is selected, this edge is selected, then this H and G, you are going to take the union of H and G. So H and G, if you take the union of here in line number 8, if this edge is selected, then you are going to take the union of U and V, means union of H and G. So union of H and G would become like, and give some any new name or same name to this. So after selecting this edge, now this node H and node G would become a single set. Likewise here in selected I and C, so before selecting this edge, I were separate set and C was separate set, but once this edge is selected, this I and C would be condense or take a union of these two. So this I and C are in same set, and give it either of the name, let's C or H, whatever. So now the next process, here you are taking the union of these three, since these edges are selected, so the union of vertices would be H, G, F. So this is a set and this is another set, I, C. Likewise here this is also included, so AB would also be included. newly elected edge there. If we consider this one, the CF edge, so it is safe, so it is included. Once it is included, so C is present here and F is present here. Now if we include this edge, so these two set would be merged, because you are going to take the union of this with this. So union of this set with union of this set, and if you are taking union of this set, the new set would become I, C, H, G, F, and then AB. Now after this we are consider this edge. Now the set of I means find out where I belongs to which set. So I belongs to this set, and find out G belongs to which set. So G also belongs to this set, same set. Since these two vertices belongs to same set, that means this edge is going to make a cycle with the previous selected edges. So that's why we reject this one. So manually we could see the graphical notation and we could see that it is going to create a cycle, but suppose imagine the situation where there are 10 lakh nodes, and how could we consider whether a newly considered is going to make a cycle or not? There should be some mechanism, and that mechanism is the set theory. So the complexity of the Kruskal algorithm would be finally E log V. Initially it is calculated to E log E, but there is a relationship like this. For the majority of the cases, the V square is much greater than E, so we simply replace this E with V. So order of E log V would be the final complexity of this procedure. So that is how all about the Kruskal algorithms. Thank you.